Why can't you take insulators to social gatherings? Because they don't know how to conduct themselves. Okay, that's enough terrible jokes for today. All right. Should we get started? All right. Hey, everyone. Welcome to Code Astro Day 3. It's awesome to see those of you in person today. Let's get started. So first off, as always, I just want to remind you about the anonymous feedback form. Please fill this out as often as possible. We'd love a continuous stream of feedback. Thanks to those of you that have filled it out so far. We've tried to implement or at least note down for next year your feedback so far. Really appreciate it. I also want to remind you about the class source vocabulary list at this doc here. So we've been updating this a little bit throughout the week. You can go check it out. You can also, everyone should have comment permission. So if you have a suggestion of a word that you don't know, that you want us to add a definition for, please feel free to go there and add that. And then once more, just a reminder about how to ask questions. On Zoom, you can ask questions in the chat box. This is a little bit hard to keep track of while we're presenting. So sometimes when I'm presenting, I don't always see all the chat box questions. But a lot of the other TAs and instructors have done a really good job of like keeping track of everything and replying. So that's a valid option. You can also ask on Piazza, and remember there's an anonymous option on Piazza. Not Slack, that hasn't been updated in 2 years apparently. Also on Discord. And we suggest that you communicate with your fellow participants this way. And we're all going to be monitoring these mediums all day. Just once more to remind you about the overall goals of the workshop. By the end of the workshop, you'll be able to use the language of software development, develop and release an open source astronomy package, and write code that follows the best practices of software development. So today we're going to be focusing on documenting code and also releasing code. So here are the goals for the workshop today. You're going to be able to use doc strings and Sphinx in order to document code for others to use. There's an optional activity at the end of today, the goal of which is to be able to profile the runtime of your code and identify computational bottlenecks. And then finally, you'll be able to set up and release your Python packages publicly using PyPy and pip. The project goal for today is to document your code and put it on PyPy to make it pip installable. All right, and then before we get started, I want to remind everyone to pull the latest version of the repository. I know a couple of folks have been having trouble with merge conflicts. So if you run this and you get some sort of issue that you don't know how to resolve, please feel free to reach out to us and we can help you figure it out so that you have the latest version of the code. It shouldn't be too critical today. I don't think we've made any breaking changes in the last 2 days. So if you can't get it working by the activities, that's okay too. All right, that is it. Matt, you're up.
Work here. Share screen. Oops, not leave meeting. Okay, great. So, okay, can everyone hear me online and everyone here can see my screens, it looks like? Okay, great. As Sarah mentioned, for the next hour or so, we're going to be talking about code documentation. First half of this hour, I have a presentation and a little follow-along coding activity that we'll do together. And then for the second half of the activity, everyone will be breaking up into their breakout groups and start working on documentation for their own projects. But first, for the first half, I'd like everyone to go ahead and go to the GitHub repository for Code Astro. where this presentation will be. Okay, so this is the main Code Astro GitHub page. Go ahead and click day 3, and then go to tutorial doc. The presentation that I'll do is under a README file here, which automatically compiles. You can start looking at today's meme, which is a lot of fun. Yeah, so this is where the presentation and the demo I'll be going through will be in this README. Now for the code along part, if you're interested in coding along with me, you're welcome to do so. In some sort of terminal window, you can go ahead and navigate to the Code Astro GitHub repository. So here's the main page. And then we're going to go to that same directory. So go to day 3.
Matt, you want to make your text a little bit bigger?
A little bit bigger? You got it. How's that? Okay. So we're in Code Astro, day 3. Go ahead, go under tutorial doc. And now we're in the right repository. Okay, so let's jump in and begin. So a little bigger for folks. Great. Okay, so I think when you start talking about code documentation, sometimes you get a reaction that looks something like this, right? But deep down, if we're honest with ourselves, we all know how important code documentation is, right? And it's not just for allowing others to use your code, it's also for yourself. I mean, I can't tell you the number of times I've written a function and said, I know what I'm doing, I don't need to document this. And then I try to go back to that a couple months later, and I have no idea what's going on, right? So there are a couple different ways you can document code. One way you can do this is by using block comments or inline comments. I think you've come across this in the workshop so far. That's where you're writing code and you have a line that has a pound symbol in front and just some descriptive text, and then you have the code immediately underneath. So this is great. This sort of commenting your code is fantastic, but that's not the type of documentation I'm going to talk about today. Today, we are going to talk about Python docstrings. So folks, don't worry about trying to read the small writing on this slide. Just I bring this up really to show the screenshots, which I'll refer to as I'm talking about. Okay, so what is a docstring? Well, a docstring is a section at the top of your function, class, whatever you're coding, that provides a top-level overview of what that code, function, whatever, is supposed to do. It's typically denoted, if this is a screenshot of what a docstring might look like, you'll notice it's usually denoted by a triple set of double quotes, kind of to start the docstring, and then it ends again with that triple set of double quotes there at the end. Now, with docstrings, there's a few different styles that you may use. In fact, I think on my README, at this link right here, if you want to learn about some of the different styles out there, you can follow that link on your own time. You can look at it. But today, we're going to talk about the Google style docstring and how it's formatted. So in this tutorial doc directory, I'll hop over here, right? Here's where we are. You'll notice that there is a function, correlate.py. And if you take a look at correlate.py, there are a couple functions that have been documented using Google style docstrings. This is a screenshot of one of these functions right here. It's the function crosscore, right? And if we take a closer look at this docstring, we see, at least in my mind, I kind of break it up into 3 main portions, right? There's this first section at the top. At the top, you start off, there's your first line, which is a very brief 1-line super top level summary of what your code does. Then after that, there's a break. And then you can have a block of text, as long as you want, to describe what your function does in more detail. Here, this is a pretty straightforward function, so that block is pretty short. All right, so that's section 1. The second piece, this is the section where you see args here. This defines the input variables to your function. All right, note that we have a description of the variable names, what those variables are supposed to be, and also, importantly, what is the data type of that variable. And I emphasize that because this is something I've overlooked myself. It's actually really valuable when someone else is looking at your code to understand what are the data types of all the variables that are supposed to go into it. That's really helpful for debugging. So easy to forget, but really important to include. All right, so that's the second section. For the third section, that's here, it says under returns, and this gives you your code outputs. Again, what's the data type, and then what is the description of whatever your code is supposed to do. So this is a typical docstring, and in this it has, I don't know, 75%, 80% of all the formatting that you'll ever need for docstrings. However, when you have specific cases, let's say you're building docstrings for a class or an exception, or if you have a function that has optional input variables, this general structure is tweaked just a little bit, just very slightly. I'm not going to talk about all those modifications here today. We just don't have time. But on this link here in the README, there's a nice link you can follow, again, on your own time, if you may, that kind of gives examples of documentation under all these different circumstances. But for now, this is the bulk of what you need. Okay, great. So let's say we've gone through, you have all your functions, you've put in the effort to make these beautiful doc strings. What's the next step? Well, now we want some way for the users to access these doc strings, to be able to search through them, and basically interact with them in an easy way. We don't want to force our users to have to open all of our .py files and search these things individually. Right? So ideally, what we'd have is some sort of web page or set of web pages that compiles all of our doc strings and allows the user to search through them as they want. Right? Unfortunately, we don't have to build these web pages from scratch. There are automated tools out there that will automatically go through your code, find your doc strings, and make these web pages for you. Right? And one of these tools, that's what we're going to talk about today. And it's called Sphinx. Okay, so now we'll go to the next part. Next part, we're going to try using Sphinx to build some documentation for our function correlate.py. So if you go into the README here, we're going to follow the Sphinx quick start guide. As I said before, if you'd like to code along with me, I'm going to go through this demo. If you'd like to code along with me, that's great. But also, if don't feel like you have to, if you don't want to, feel free to also just follow along with the README, because there's lots of screenshots and shows everything what you'd like to do. But okay, so to get started here, let's see, can everyone, is the writing large enough on my terminal window for folks to see? Okay, great. Okay, so the first thing we need to do is make sure we have Sphinx installed. See, this is first line here, pip install Sphinx. I've done this already, but yeah, we'll just make sure everything's installed. Great. And on top of Sphinx, there are these two packages, Sphinx Contrib Napoleon and Sphinx RTD Theme, that I'd like you to pip install. I'm not going to talk too much about them right now. We'll come to these in a little bit, but we can go ahead and pip install them down there. Okay, great. Now we are ready to get going. Clear. Okay, so how do we build the documentation for correlate.py, which is this function right here? Well, the first thing you need to do is make a docs subdirectory. Right, this is where all of our documentation is going to live. So I'm going to make dir docs and then cd down into it. Right, so now I'm located in docs and it's an empty directory. And here in this docs directory, this is where we are going to run Sphinx quick start. And if all goes well, it'll start and you'll see something that looks like this. Great. So this first question you'll get, separate source from build directories. Don't worry about that too much right now. It just has to do with how your files are going to be structured. For the sake of this activity, let's just click no. If you're curious, you can experiment with that later. And then after that, you're going to get some more questions like, okay, what project name do we want? Let's go ahead, we'll do correlate. Who are the authors? There we go. And then it's going to ask you a question about project release. So I'm not going to talk too much about numbering systems like this before. I think the next lesson that I think Sarah will do on code release, she'll talk a lot more about versions. But for now, you can put any number you want. Okay, and yes, I want to build the documentation in English for now. Okay, so here we go. We've run the quick start guide. And now if you look in your docs subdirectory, you'll notice that Sphinx created a bunch of these files and directories. We're not going to talk about all of them today, but there are a few that are very important that we're going to have to make some modifications to in order for this to work. And the first function to look at, the first file to look at is this one right here, conf.py. This is a configuration file for Sphinx. So we can go ahead, we can open conf.py in your favorite text editor. It can be VS Code. I'll be honest, I'm not great at VS Code. I'm an Aquamax person, so I'm gonna, for the sake of the demo, I'm gonna use, oh, oops, actually I had all these open already. Let me close, did not give things away. There we go. So I'm gonna use Aquamax to open mine, but again, it doesn't matter. All we need is a text editor. And if you open conf.py, you should see a file that looks like this. Okay, so what do we need to do? So the first modification that we need to do to conf.py is we need to set up the path. That's this top section right here. Now, what is the path? The path is what tells Sphinx where to go on your computer to find the .py files that it needs to compile. All right, so in order to do this, we're going to uncomment these lines, import OS and import sys. Don't worry about that. Those are Python modules we need. And critically, it's going to be this command here, sys path insert blah, blah, blah. All right. Okay, so what we want to do is we want to modify this part of this command, the path abs path, to point to the path where the .py files are that we want to document. For the sake of this activity, right, we're living in the docs directory, and the code we want to document is correlate.py, which is located in the directory above us. So we can go ahead and just say, okay, put the directory above us into our abs path there. Okay, now your path is set. Next, oops, sorry, scrolling a little too fast here. Next, we're going to modify some of the project information. You'll see some of the information we added earlier. Well, we need to define for Sphinx what the main page of our documentation is going to be, what the root page is going to be. And so for that, we put this command root doc, and for now, set it equal to index. Now, what is index? Again, if we look at these files that Sphinx made, you see there's an index.rst. I'll talk about that a little bit more, but that's going to be the main page of our documentation. So root doc equals index. That's just saying, okay, look there for the main page. Oh, question, yeah.
Can you explain what this path insert command was, and then when it wouldn't be just double dot?
Yeah, that's a great question. So sys path, so the insert, it's what the command is doing. It's saying insert this path into your string. Actually, insert this string into your path. In particular, you see that that 0 up there. That's saying actually put the string in the front of your path. It's the 0th element in your path. Now, when in this case, it's a double dot. That's kind of shorthand that we're doing right now, but you can point to it. It doesn't have to be, we call that a relative path because double dot is relative to our current working directory. It doesn't have to be, you can set it to an absolute path. So an absolute path is something like /users/ blah, 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 blah. All you have to do is make sure that wherever directory your .py files are, that's what you put in between these quotes. So if we wanted to, I think this will work. I haven't tested it, but we could, put the full absolute path, something that looks like that. And in fact, maybe that might be a little bit more formally correct because it's just, less ambiguous. Sorry, did I answer your question?
So usually our docs file will always be like one directory separation from our .py files. So this would, the dot makes sense, but it's not always.
It doesn't have to be, exactly. Most of the time your docs direct. Oh, sorry. So the question was, is our, in this example, we have our docs subdirectory, it's just right under the directory where the .py files are. That is usually standard. That is what we use. That's kind of common. So that in that case, the .dot thing will work. But you're right, it doesn't strictly have to be. And in that case, yeah, you would use these absolute paths. Other question?
If someone downloads your package, then that absolute path wouldn't work anymore.
Well, see, so the docs subdirectory, that's going to be part of your code repository. So when you download the code repository, it's already, the docs directory is already included in there. So basically, that docs is always going to be one directory below where your .py files are because it's all included in the GitHub.
But it would only work if you have the relative.
Oh, that is a good point. So maybe, very good point. Okay, I guess that's the danger of doing absolute paths. You're right. If some random person were to download our GitHub repo for the documentation, obviously they don't have the /users/ MW Hosek thing. You're right. You'd want to use the relative path. So maybe I'll backtrack what I said earlier. Maybe that relative path is always what you want to do to make sure that link always works. Thank you. Great questions. I really appreciate it. Thank you. Okay. I've answered everything. Okay, so that's the path part. And now we've established we always want to do relative paths there, not absolute. Phew, okay, good. Okay, so the next thing to modify is extensions here. We need to add some extensions in order for Sphinx to work. We're going to use sphinx.ext. Okay, so the first extension to add is sphinx.ext.autodoc. This is the extension that gives Sphinx the power to automatically document, search your code, and automatically find the doc strings, which obviously we want it to do. So we're going to add that. We are also going to add a second extension called sphinx.ext.napoleon. Now, where does this come from? If you remember in the beginning, I had you pip install those other two packages. One of those is the Napoleon package. The reason why we need it is because natively, I'm pretty sure, Sphinx doesn't understand how to interpret Google-style doc strings. So by using this Napoleon extension, it allows Sphinx to understand Google-style doc strings. So it just, tells Sphinx, okay, this is how we do what we need to do.
So using Napoleon and Autodoc, wait, so did we have to install that separately, or does that get installed?
Okay, so the question was, do you have to install Napoleon and Autodoc individually from pip install Sphinx? So Autodoc, I don't believe you have to. In terms of Napoleon, though, you do. So if we hop back to the quick start guide, you see step 2. There was these two packages here. That's where Napoleon comes from. And you'll see there's a second piece that we're going to go to now as well. Actually, that Sphinx R2D theme is going to pop up right over here. Find it? Oh.
We had a question on the chat, and just sort of moderate the pace a little bit.
Slow down. Okay. Yes. Thank you for the comment. Okay. Yeah, and feel free to put up in the chat if I'm going too fast or slow down, and yeah, just let TAs know, and then they'll let me know. This is hard for me to monitor up here. Okay. Great. Okay, so we're modifying this conf.py file, right? We set up our root doc, the index. We set up these extensions, Autodoc and Napoleon. You kind of see them right there. The last thing to modify is this command down here. It says HTML theme. All right, this is a kind of cosmetic, aesthetic, aesthetics here. This is what is the format of your web page? What do you want it to look like? For the purpose of this activity, you're going to change that to Sphinx RTD theme, just like that. Sphinx RTD theme. This is the second thing that we pip installed at the beginning, right? And it's just RTD stands for read the docs. It's just, it looks pretty. I like it. You don't have to choose it. In fact, if you're following along with the README, I think, yeah. So we're in step 7 right now, modifying conf.py. This last bullet point, you'll see this hyperlink you can follow. There's a bunch of different HTML themes you can use, but we'll do RTD thing here. Yeah, and yeah, and for folks following along, if you do get lost, check out the READMEs. I do have these screenshots showing where to make modifications. They look like that. So hopefully that'll help keep everyone together as well. Okay, awesome. That's the last modification we have to make to conf.py. Okay, so let's go over to our documentation now. And now we can actually try for the first time to compile our Sphinx documentation. All right, so the way we do that, right, we're in our GitHub repository, right? We're in the docs subdirectory where we've been working all along. We are going to type the commands make HTML. Oh, actually, there's no underscore, sorry. Make HTML, right? That's going to tell Sphinx to read the conf.py file, and if everything goes well, you're going to see responses that look like this. This is now building our documentation webpage. Great. Okay, so this has worked. Phew. Coding live is always a little bit of a risk here, so I'm glad this worked. Okay, so what happened? Well, now what we've done is we have created files and if we look here, you note this, there's this /build directory here. Well, if we look at /build /HTML, we'll notice that there's a bunch of HTML files in here that didn't exist before. All right, this is what Sphinx was creating. So let's go ahead and in your favorite text editor, or sorry, in your favorite browser, let's go ahead and open what our main documentation page looks like. And that's index.html. So there's build HTML, and you should now have a file that says index.html. Here, and if you do that, right, we have what looks like the start of a true documentation page for your software. You know, there's a search bar, there's a bunch of nicely formatted. Yeah, so this is a great start. But if you look, yeah.
I got does not exist.
Does not exist
the
under
file-
make HTML.
The file, all the lines at index.html does not exist.
Okay, did you? Okay, so let's see. So did you modify the conf.py file as we did?
Yes.
Okay.
We can also try to debug it.
Yeah, actually, for the sake, maybe we'll try to debug. Let's use Piazza and Discord to debug. It should be actually. Simon, did you have a?
Yeah,
Oh, it was-
doesn't work.
Oh, you have to open it manually.
Yeah, because you have to open to your file browser and get to that application. But we can
Okay, yeah.
debug all this during the activity.
Yeah. Okay, we'll bring back. If folks are having trouble opening, yes, thanks. So this open thing I just did, I guess that only works on Mac. Thanks for pointing that out. I didn't realize that.
Okay.
You can
run
open.
it in Finder and it works.
Exactly. You can open it in Finder or whatever, you know, file browsing service. Open it there. Okay, so we're almost there. Oops. But if we look at this documentation, we notice there's nothing about correlate.py in it quite yet. So let's go ahead and do that. Okay, so let's. Oh, whoops. No, I deleted my README. Sorry. Let me. Went too far. Okay, here we go. Sorry about that. Okay, great. Okay, so now we're ready to actually, we're starting to make our Sphinx page. Now we're ready to actually make a page for correlate.py. Okay, so the way we do that, what Sphinx is doing when it's compiling its HTML files is it's reading these .rst files that you place in the docs directory. What does .rst mean? That stands for restructured text. It's just a fancy form of text file that contains additional formatting options. Okay, so let's go ahead and let's open a blank file called correlate.rst. And we're going to make this file inside this docs subdirectory. Okay, we're going to start it off as being blank. This is where we're going to build the correlate page. What do we put in this file? If we go around, we're in, for those following along with the README, we're in step 9. And if you look at step 9, you'll notice that we have a block of text here, a code block. This is the text that we want to put inside correlate.rst.
Sorry,
So I'm just going to copy and paste it. Yeah.
is this a different folder that where like which folder is it supposed to be?
Great question. So the question, where does correlate.rst comes from? Or where does it live? So where it lives in your your docs subdirectory. So it's in the same directory as where it's same directory as conf.py is. So here. Oh, okay. I think,
We can try to figure out individual.
yeah, individual debugging. I think we might have to do it again because there's might be too many individual things to issue here. And if you do get lost, again, you can kind of follow along with the README. There are screenshots you can kind of follow along, even if you can't get it to reflect on your own sheet. Okay. Okay. Well, we're building correlate.rst. All right. This is what the file should look like over here. Now, what do all these things we just copied and pasted into here? What do they mean? Okay. Let's go line by line. The first line here, this correlation, you can think of that as a label for the web page that you're going to create. Right? In the future, if you're building multiple web pages, if you wanted to build a hyperlink to this page, you could refer to it by correlation. Don't worry too much. This is like /label in LaTeX when you're labeling figures and tables, if you're familiar with LaTeX. Don't worry too much about this line now. We're going to talk more details about that later. So, but just know that's just the label of the file. Okay. Then these lines here, this defines kind of the text on your web page. This top line, correlation functions, followed by the underscores there. That's the title of the web page. And then function to perform correlations, that's just, additional text to describe what's going on. Right? But the meat of what's going on in correlate.rst happens in these two lines here. Right? So what do these lines say? We have this like ... space auto module : find correlate. What that's saying is that's giving the command to Sphinx to go inside correlate, that's your correlate.py file, and automatically document all of the functions and classes that have doc strings to them. Specifically, it's like auto module automatically read all the members of correlate.py and document that. I have more details about that function at the end of the demo. You don't have to worry about that too much more right now. You do have a lot of control over auto module, but for now, we're just using auto module. Okay, so we're almost there, I promise. We have like only 2 more steps. Okay, so now we have our correlate.rst, should look like that. The last thing we need to do is we want to add correlate.rst to our main documentation page, right? Our index page that we said. So we are in, again, we're still in the doc subdirectory right here. We want to open index.rst. Index.rst, this is the restructured text file that Sphinx is reading in order to make the HTML page. Okay? And this stuff all here, this is what Sphinx automatically creates, right? So you should see something like that. The only thing we need to do from here is we need to add correlate.rst. We want to add that file under this command right here. Okay, what is this command? ... space top tree : top tree, that stands for table of contents tree. So what that's saying is put all the .rst files, Sphinx, it's telling Sphinx, all the RST files that it finds under the top tree command, go ahead and put those files into your table of contents for your documentation. So we only have one page for correlate.py, but if you would have another, you can put as many whatever .rsts that you have, but you would all list them right here. Just one note, when you add correlate.rst, note that you have to match the indentation level of these other 2 commands here. Max depth and caption, don't worry about them now. I have some more information about that at the end. Just note that the captions have to line up. There, the indentation there has to line up. Okay, now we're done, we're set. And here's the payoff, right? We've made our correlate.rst file. We've added it to our index.rst file. So now, if we go to our doc subdirectory, let's rerun the command make html. And hopefully, if all goes well, it'll work. And now, let's go ahead and reopen the index.html page that was created. So I'm going to use this open command, but remember that doesn't work for everyone. I guess it only works on Mac. I apologize for that. But where index.html, where that was created, right, under the /build HTML index and index.html. That's where it is. Let's open it here. And now we have our documentation page again. But if we look under the contents, there's our correlation function. And now if we click on that link and open the correlation function web page, we have this beautiful web page all set up. Here are the names of our function. And Sphinx was able to go in, automatically read our Google style docs, and you can see how nicely formatted this is. Right now, well, yeah, I mean, a lot easier than trying to read through individual readmes and .py files. Yeah, and there's a lot here, right? There's an index that describes, what's the name of all the functions I have. There's, again, the search bar is now active, right? So this is now this is great, right? We have built a Sphinx documentation page now for our correlate.py. Okay, awesome. So I know there was a bunch of questions in the chat. I guess as TAs and instructors, we'll try to debug them as we go along. But before we break into the activities, I just wanted to point your attention, if you're looking at the README, under the Quick Start Guide, you'll notice there's a section called Tips and Tricks. I'm not going to go through all this now, but I'd encourage you to do it in your groups because there's a lot of useful information down here. In particular, what I will say, like especially this first bullet, talks about additional examples for what doc strings look like. I talked about that earlier for classes and exceptions and other things. And also, it includes a cheat sheet for how to format your web page using .rst files, right? Like how do you make subheadings? How do you make lists? How do you bold, italicize things? That's all under the cheat sheet. And finally, just a warning, doc strings and .rst files, they're very finicky regarding syntax. The spaces, the indents, the punctuations, it all has to match in order to work. So if you're trying to run this and it fails or something, definitely check the syntax. That's, in my experience, that's often the place where it fails. And then I have some information here about some of those Sphinx functions I talked about briefly. If you wanted to learn more information about them, you can go ahead and read that with your group. Okay, so now I think I'd like to take the next half hour, and is that okay? Oh, quick question, yeah?
So, index and RST versus what is that?
There's that word, ref? REF? Okay, that's a good question. So actually, I have a screenshot right here, or code text right here. So this is under the tips and tricks. Repeat the question. So there was a quick question, what the :ref: syntax, what does that mean? You'll see that in the index.rst file. It also comes up, you can see it in the last bullet here in tips and tricks. That is how you can reference other web pages in your documentation. Remember, I talked about that top line in correlate.rst. It was a label, right? So you basically take a look at that bullet point, and that'll kind of describe the .ref, .ref, . That's how you call those labels. And there's a little example on that page there. Okay, so for the next half an hour, I think let's go ahead. Let's break out into our breakout groups and locally our local groups. And let's work on building Sphinx documentation for your Python repos. What we'd like you to do, one, document at least one function in your package using Google style doc strings. Ideally, you do it for everything, but do it at least one. And then once you do that, go ahead and try to set up Sphinx documentation for your project repo and build the doc page, just like we did for correlate.py. And if you need a hint on where to begin, remember the place to start is always you go into your repo, make a doc subdirectory, navigate into it, and then you can run the run the Sphinx quick start command, and you can follow what we did in the guide and just do that for your own packages. And finally, if there's time, and no worries if you don't get to this, this is only if you have time. If you're finished with your documentation, try trading it with another group. I guess that's a lot easier to do for the in-person folks, but try trade documentation page and see if another group can understand the documentation that you wrote. Right? Because remember, at the end of the day, we're writing this documentation for others to be able to understand how to use it. Yeah, so question before we break out.
To be able to share it with another group, we actually have to give them the HTML files because this isn't actually posted anywhere.
Yeah. Oh, this is actually, I guess this was a little easier when we were all remote and sharing screens.
Laptops and have them read it.
Yeah, let's do that. Sorry, that's actually a little bit of holdover when we're fully remote. This was a little like sharing screens and stuff was a lot easier fully remote. But yeah, okay. If you're in person, swapping laptops might be just the easiest way to do that. But again, only if you get there. I expect that it might take a lot of time to set this up. But okay. Well, thanks so much. Again, half an hour. So I guess 10 after the hour. Yeah, let's go ahead. We'll meet up again, and I just have a quick 5-minute wrap up at the end. So thank you, and feel free to ask all of us when you have questions. Thanks. Awesome. I guess we got right after.
All right, everyone. Welcome to the session on releasing code. This is one of my favorite sessions to teach in the workshop. We're going to teach you in this session how to get everything able to be uploaded to PyPy and able to be pip installable. As Jason would say, let's take a minute to appreciate the meme.
Let's be honest, y'all.
So the trick to making code pip installable and able to be uploaded on pip is that there's basically just a set of instructions that you have to follow. These instructions can be kind of finicky. You'll probably run into some bugs and issues, but there's nothing like deep and difficult about it. It's just there's a set of instructions to follow. All right, so the goals for this lesson are that by the end, you will be able to state the purpose of setup.py and init.py license and README files. You can be able to package a Python project for broad distribution and make your code publicly available on PyPy, and also understand what all those words mean. So I just want to give you a sort of snapshot view of what the activities for later today are going to be. You're going to start by creating setup.py and init.py files for your package. You're going to package and upload your code to PyPy using Twine. You're going to release your code on GitHub, create a Zenodo DOI for your package to make it citable. And then optionally, if you have extra time and you want to have a little bit of fun, you can add badges to your README file. So just in case you're wondering, this is what badges look like. I love badges and buttons and everything. So these are little badges. An example of one is the docs are building. So if you click on this, it links to the documentation, which you now know how that's built. I also want to emphasize that even if your code isn't ready, quote unquote, to be released, even if it's buggy, even if it's unfinished, we still encourage you to make an initial release and go through all this process of actually releasing your code. This is a really low stakes environment. It doesn't need to be perfect. You can create several releases. And it's also important to practice the process of releasing your code. So push yourself to go for it, even if you're a little bit scared and you don't feel like your code is ready. All right, so let's get into it. First of all, why bother releasing code? The files that you have to add in order to make your code pip installable give you control over how your code is set up on other folks' computers. So right now you have maybe a Git repository that's uploaded on GitHub, so other people can access your code. But say you want to add certain like put data files in a certain place on someone's machine when you're installing it. This is something that you can do with PyPy. Sorry, with pip. You can also do version updating this way. So similar to the way that commits create a checkpoint that you can go back to in your own code, versions create checkpoints that your users can go back to. So if something breaks, they can say, okay, well, it was working in version 1.2.3, so I'm going to reinstall that version and figure out what went wrong in the meantime. It also just in general sort of streamlines the process of installing and using packages. I think probably at this point, everyone here has lots of experience pip installing things. It's really nice to be able to pip install and not have to worry about paths, not have to worry about, I mean, of course, we all know you do, in fact, have to worry about paths and all that stuff anyway. But in theory, you don't have to worry about all that stuff. All you do is pip install, and then you can import and use the package. Okay, so I've been using this word package. I think probably by now most of you have a sort of intuitive idea of what a package is. Here's a formal definition. A package in Python is anything that's installable. So packages package related code together in one place. You've also probably seen this dotted naming scheme whenever you're importing stuff. So you might do like import orbitize.utils. The reason for this is that this prevents namespace conflicts. So if Orbitize has a module called utils and Radval also has a module named utils, if you were to just If Python behaved in a way that you imported everything from Orbitize and imported everything from Radvel, then it would get confused which utils to actually use. And this is an issue in some other languages. Not every language has this sort of dotted, this namespace conflict prevention system. So this is a really nice thing about Python. So what's the difference between modules and packages? A module is any Python file. A package is a collection of Python files within init.py at the root or at the base directory. So remember that a package is anything installable. So I'll get to this in a minute, but init.py is the thing that actually communicates to the thing that sets up the code that this is a Python package, and I need to install it in such a way that you can import this thing that has an init.py at the root. So here's a diagram of the sort of least information to the most information of all the different words I've been using. So variables have the least information. You're going to have the most variables in your code, then functions and classes, then modules, then packages. So a module is made up of several packages. If you have several different files, Python files that have different functions and classes in them, each one of those files is a different module in Python. So confusingly, Python treats packages and modules both as type module. This is because in Python's mind, all modules are packages, but not all packages are modules. It doesn't really matter that you understand why that is, but just note that, I know, right? Jason just did this. But note that if you run the following in an IPython IPython shell, what is it, terminal shell, IPython, this is what you see. So Orbitize itself is a type module, and orbitize.kepler, which is one file within the Orbitize package, is also a type module. If you want to learn more about this, you can read through this thing here.
I'm just a little confused. So when we define a package, so let's say in this case Orbitize, is it going to be like a super file that has a list of files within it? Like, or is it more like a directory file structure?
Yeah, good question. So the question was, when you define a package, is it sort of one file that contains a list of all the other files, or is it like a directory? So I'm about to get to that. On the next slide, I'll sort of walk you through the structure of what packages look like. Okay, so here's an example package. So these things that have slashes after them are directories, and then anything that ends in .py is an individual file. So you can see that sound here is a top level package, and it's got an init.py file at the root. It's also got a couple of sub packages. So each of these are just directories, and they each have their own a bunch of Python files in them as well. So waveread.py in this case is a module of the sub package formats, which is a package of sound. Does that answer your question? Okay, cool. So if you pip installed this package and you wanted to import the functions in Echo, the way you would do it is from sound.effects. So the overall package, then the sub package, import the module name. And then if there was a function within Echo, say the function was called like printhello, you could then use that as echo.printhello. Okay, so I'm going to go through a bunch of the different types of files that you need in order to make a package. I'm going to highlight each of them in purple because I like purple. And yeah, so just to make an analogy between this sort of overall map of what the next couple of slides are going to look like, this line here means that it's at the root level. So that would mean it's at like just within sound, for example. License README requirements would all be at the same level as this first init.py. And then this indent means that this is these are files within this subdirectory. So in this case, my package is the overall like Git repository. the exact same name directory, my package, is a subdirectory that contains all of your code files. Then there's a bunch of other files in the root of your directory, a license, readme, requirements, setup.py. Then you might have a separate test directory, and I didn't list it here, but you could also have a separate docs directory. All right, so let's talk about init.py. Excuse me. So an init.py lives in the same directory as your code files. It's sort of analogous to the init method of a Python class. So the init file is, the commands in the init file are executed whenever someone imports your package. And this is also the thing that communicates to setup tools, which I'll talk about in a little bit. That's the script that actually installs an executable for your code on someone's machine when they're pip installing it. Init.py tells that program that this thing is a Python package. So I'm going to do a quick little demo. First, I'm just going to show you what the init.py file looks like in Orbitize. And then I'll also modify it so that you can see it actually running in real time. Just give me a sec to open up VS Code. Okay, so just to orient you a little bit, this is the GitHub of everything that's on GitHub, the Git repository for Orbitize. We've got another subdirectory with the same name, Orbitize, that has all of our modules. There's also a docs subdirectory where we've got all of the stuff that you all just got very familiar with. We've got a test subdirectory. We'll talk more about testing tomorrow. There's a bunch of other stuff you don't need to worry about for now. So let's look at, in Orbitize, the subdirectory that contains all of our code. There's an init.py file. There's a couple of things that happen here. First, we define a version. We'll also define a couple of other like Orbitize, like top level environment variable type things. Let me show you how this works. Come on, terminal, you can do it. All right, I'm going to open up an IPython environment. Okay. Yeah, thanks. Is that better? Okay, sweet. So when I import Orbitize, you can now see that if I do orbitize.datadir, it prints out this data directory. So you can see that this datadir variable has been linked in this case to orbitize.datadir. So all of these commands in this file will be executed. You can leave this blank. You don't need to execute any commands when you import your file. But if you want to have any like top level variables defined, this is a good place to do it. Just to prove to you that this is actually that all the commands are executed, I'll have it type something. What should I print? No, Snoot was yesterday. It's in the past. What? I'm a real boy. I love it. I'm a real boy. Oh, I guess I'm gonna. Oh, there's something in the chat too. Blord. Okay, we'll also print Blord. Print. Okay, I'm gonna reload IPython. Now, if I remember to, there we go. So when we import Orbitize, it now prints out I'm a real boy in Blord. So anything you want to do to sort of set up the package, you can do here. Yeah, definitely. There's a comment that it's useful because you want to know if it actually imported something or if the changes you made actually got propagated. So yeah, definitely. Okay, let's go back to the slides. Yep, question.
So in this case, like for example, maybe within Orbitize, you want every single file to know what numpy is. Would the init.py be the place where you do that? Or would you still have to import it on each separate
You would still have to import it on each separate Python file. Yeah. So thanks. The question was if you want every single file within Orbitize to know what numpy is, would you do that in init.py? And the answer is that you would have to do that at the top of each file. So you'd have to import numpy in the imports at the top of each file. I think there's probably a convoluted way to do that in the init.py, but I would not do that. I'd just do it in the individual files. Okay, so we've talked about init.py. Let's now talk about setup.py. Setup.py is, it lives in the root of the repository. So it lives here along with, at the same level of your package with your README and your requirements. It specifies how the code will be built on a new machine. So we, just like everything else, there's a package that builds everything automatically for you. We use something called setup tools. So in order for setup tools to run, this is like sort of the minimum script that you need. You import setup tools, and then you run this setup function. You can specify the name used to import your package here. So that's what tells pip what to import. You can specify a version here, and you can also use this find packages method. That'll basically just go through, find everything that has an init.py and make that importable. So there are two commonly used packages to help you write your setup.py file, which was something that confused me for many, many years. So as far as I know, everything that I found online says that distutils is basically no longer maintained, like less feature-rich version of setup tools. So we encourage you to use setup tools, although you might see some other packages using distutils. All right, so we've talked about init.py, we've talked about setup.py. I should also mention too that once you have a setup.py file, your code is pip installable. So it's not necessarily on pip, but if you run pip install dot within the directory, it will know how to install it on your machine. So that's all you need is just that setup.py file. Okay, so let's talk about license and README files. These are two files that if you create a new repository on GitHub, it'll create for you automatically and walk you through the process of choosing. So the README file is what users will see when they open your package. And the license file is some legal stuff that I don't know a lot about, so I'm just gonna say, don't listen to me about it. You can follow this link. I really like this link. It sort of takes you through, like, if you want to use your code for this purpose, then you're better served with this license. Yeah. I also want to show you the Orbitize and Radbel READMEs, so you can see what those look like. Okay, so here's what the Orbitize README looks like. It's pretty minimal. The file lives here in the root of the repository. And then it just shows up whenever you open the GitHub page at the bottom. The Radbel one is a little bit more, has a little more stuff in it. I don't think I have it in my recents. So the Radbel one has some other stuff, some features, gives you directions to tutorials. You can put a lot of different stuff in there. Okay, I wanted to show you something else, but I forget what it was. Oh well. All right, let's next talk about requirements.txt. So, yep, question.
And do you have any guidelines for like things that really need to be in the README? Like, you know, it's the first thing that you see when you open up a package. Are there guidelines for what to put in there?
Yeah, that's a good question. So the question was, are there guidelines for what to put in a README? Honestly, I generally prefer, like, I usually put like installation information and tutorial information and stuff like that in the docs. So I usually just use the README as like, you know, a place to link to the docs, and for badges, because I think they're fun. But I think if you're not going to put that information in the docs, putting installation and like how to get started using the code is a good thing to put in the README. Anyone else have thoughts about that? What should you put in the README? Okay. Yeah.
I think it's one of these things where you look at your favorite packages and see what they put, and you're like, I like these things. And I like those things too.
Yeah, definitely. Jason said, look at your favorite packages and see what they put in the README. Yeah, good question. Thanks. Okay, so we're talking about requirements.txt. This is a list of Python packages your package needs to run, or dependencies. So anything you import in the top level of your Python packages that isn't installed in a Python environment by default, you need to add. So some things are, like sys, for example, the sys package. You don't need to have sys as a dependency. If you need to test out which packages are automatically installed, you can create a fresh conda environment and just try to import something. If it's there, it'll work. If it's not, you need to add it to your dependencies. So I'll show you what the orbitized one looks like. Or I'll show you the Radbell one because it's right here. So this is what it looks like. It's just a list, a text file of all of the different packages that Radbell depends on. You can also optionally specify versions of these packages. So in this case, we're saying that you need version greater than or equal to 0.23 as Python. But you can also just include, okay, I just need DIL, any version will do. So the question in the chat was, this is in addition to having import numpy as NP in each module, for example. Yes, exactly. So that's separate because this is the thing that communicates to, so you can do pip install and add in a -r flag with requirements.txt. And that says to pip, okay, I'm gonna install all of the requirements first, and then I'm gonna install your package. So importing numpy at the top of your file doesn't install numpy, it just imports it and like puts it into the namespace for you to use. It doesn't say like, this is the thing, it doesn't do anything about the installing. Another question in the chat was, do you have any advice when trying to figure out which versions of packages are compatible? That's a very good question. I wish I knew the answer to that. Not really. Trial and error. Any other suggestions for that one? Yeah, Jason?
I put in the chat that I generally don't put version numbers unless I need it. Like unless it breaks something, I generally just leave it, like whatever. Just empty. You don't have to put a version number.
Yeah, good advice. Yeah, generally, if a package has a version number specified in a requirements.txt, that means that some other version number broke the code. So they said, okay, we need this in order for it to work. Okay, so this is all you need, basically. So here are some instructions for testing your installation locally, so just on your computer. So once you create your setup.py and init.py files, you should be able to pip install your code. Pip installing your code means that your code, the setup tools script creates an executable, something that can be run, and puts it somewhere else on your computer so that you can import it from any Python and from any place on your computer. So if you cd out of the directory that you're using to build your code, you should still be able to import that code. So the way you do this is you first cd to the directory containing your setup.py script, and then you type pip install -e dot. So pip install dot means run the setup.py script for this directory. So it'll look for a setup.py file and then we'll execute whatever's in there. The -e flag means that anytime you make a change, it'll update the installation. So you don't have to reinstall it every time you make a change. So this is really handy for developers. This is actually what we had you run when you installed Orbitize on disk at the beginning of the package. So if everything goes well, your package will be installed, and you could just open up an IPython environment and import it from anywhere on your computer. So I think what a lot of you are here to learn is how do you make it publicly available? So I can pip install this on my local computer, but how do I make it so that anyone can pip install this? So you can do this with PyPy. PyPy stands for the Python Package Index, which is a software repository for package written by the Python community. So PyPy is the place that packages go that are able to be pip installed. Pip, which annoyingly stands for pip installs packages, which is horrendous and I hate it. Just kidding, I love it. So pip is the package installer tool associated with PyPy. So anything that is hosted on PyPy is able to be installed by pip. So a question that we often get at this point is what's the difference between pip and Conda? So Conda is actually a general purpose package management system. And it's harder to get things hosted on Conda than it is to get things hosted on pip. So bigger tools that are in very wide use like NumPy and SciPy are available on Conda. My packages and your packages will probably be on pip. Conda also like manages your environment. So you can do like the Conda activate stuff that you all have been doing. That's something that's distributed with the Conda system. There's more on pip versus Conda at this link here. Take a minute to appreciate the meme. All right. So we're going to recommend that you upload each new version of your package to PyPy. That means not only that people can install the latest version of your package, but they can uninstall any previous version of your package. So if you want to pip install version 1.3 of Orbitize, you can do that just as easily as installing version 2. Whatever. Just like anything else in this course, there's another useful tool for uploading stuff to PyPy. We're going to recommend that you use Twine. Twine, in my experience, is super easy to use. It's like 2 commands to build and then upload it to Twine and then upload to PyPy. And there's a little getting started guide here. So I'm not going to go through this right now, but if you all run into issues with it as you're working on this, please feel free to ask. All right, so Matt promised that I would give you all a crash course in version numbers, and I'll also talk to you a little bit about what versions and GitHub releases are. So there are several different things that I do whenever I make a new version of my code. First is I pull all those changes to the main branch, make sure that main on GitHub reflects all of the changes that I want to be in this new version. I then upload this new version of the code to PyPy so that people are able to access it. And then I also do a GitHub release. So this is like a way of tagging on GitHub specifically which versions are which. So every time you make a significant change, we suggest releasing a new version of the code. It's totally fine to release lots and lots of versions. Like sometimes people think like, you know, I shouldn't release the version until I make a huge change. I basically release a new version for everything that is going to affect a user in any way. So if I like fix a typo in the documentation, I wouldn't release a new package, a new version for that. But any sort of bug or something like that is something that I'll release a new version for. This link here takes you through the process of doing a GitHub release. It's also sort of just like a click along type thing. It's, in my experience, not too difficult to get started with. Some best practices for these things, since you have 2 separate ways of maintaining different releases of your code on PyPy and GitHub, it's really important to keep these releases consistent. Actually, one of the worst bugs I ever found in my whole life was because a package that my package depended on had different versions of their package on PyPy and GitHub. And I have never been more angry in my life. It took me hours and hours to figure that out. So that's not a common thing. I've only seen that happen once in my entire life, but don't do that. I'm gonna find you. Another good practice, something that Matt also mentioned in his lesson, is to maintain a descriptive change log somewhere in your docs so that you can say, so that people can not only know like there is a version of the package here, but know what changed between each of the different packages. So I'll give you a little show and tell of our change log for Orbitize. So we've got just the version number, the date that it was released, and some description of everything. So this is fun. I'm proud of it. All right, and then version numbers crash course, which was something I learned when I was writing this lesson for the first time. If you make a major functionality change, especially if backwards compatibility is lost. So backwards compatibility means that if someone tries to, if someone wrote a script with your package and then they tried to run it with the new version and it broke, that's called losing backwards compatibility. So if there's a major change, and especially if backwards compatible scripts aren't going to work, and if scripts aren't going to be backwards compatible anymore, if your package isn't going to be backwards compatible anymore, that's when you would increment this first number. We also generally, the first big release, like so if you're working on a software package and you are sort of getting it all ready and then you're ready to do sort of the first big one, generally make that version 1.0. So you can have several like pre-version 1.0 releases that are like 0.9 or 0.1 or whatever before you do version 1. The second number is a minor functionality change. So if you add a new feature, you change something sort of small about the code, but it's still gonna affect people. And then the last one is a bug fix. So for example, if I released, the first fully working version of my code, I might call that 1.0.0. I then immediately find a bug, as you always do after you do a big release like that. That would be version 1.0.1. And then if I add a new feature, like say I add a module for plotting, I might make that version 1.1.0. Another tool that I want to walk you through is, excuse me, is Zenodo, which is a way to make your code citable. So you don't have to write a paper in order for someone to be able to cite your code. Zenodo is a really nice way to do this automatically. There's a, again, I included a little link to get started with Zenodo and set it up by yourself. I'm also going to show you what the Orbitize Zenodo page looks like. Zenodo. Oh no, I always try to do this. I can only get to Zenodo through the badge, which is one of the great reasons for having the badge. So make this little badge here, which is nice. So this is what this looks like. There's a separate Zenodo page for each version, and you can configure it so that it automatically makes a new citation every time you release a new version of the code on GitHub. It has a zip file containing all of the code itself. So if someone wants to like download the contents of your Git repository, they could do that here. And then also at the bottom, it's got like nice bibtech-ified versions of these things. So someone could just paste this into their citations inside your code. Okay. One of the last things I want to talk to you about is publishing software papers, like what the sort of purpose of that is and how you could go about doing that. So first, I just want to note that it's worth making your code open source, even if you don't plan to publish a paper associated with it. I also, even if I'm like not releasing a package, I'll still just like make my scripts or something that I use to make like plots and stuff. I'll usually just make that open source as well. However, if you do release a big package that other people can use and maybe can use for, I think that a good metric is if you think your code will be able to be used by multiple people for different purposes, then you could think about publishing a software paper about this. It's good advertising to publish a paper about your code, and it also gives some people something else to cite when they use their code for your own work. So I linked some examples of software papers in astronomy that you can check out. I also wanted to just plug our TA, Paulina's excellent notebook in Spanish. If you speak Spanish, great. If you don't, learn it so you can read this notebook. So Paulina actually hosted her own version of this workshop and wrote a lot of excellent tutorials taking you through a lot of these processes. So she's got a really nice Jupyter notebook going through all of this stuff as well. All right, so it's 11:16. I think let's take half an hour to do this as well. What do you think, Matt and Jason? Okay. Okay, so let's take half an hour, get started releasing all of your code, and then don't worry if you don't finish. Feel free to continue later this afternoon. Good luck.
I can make
Yeah, we're gonna wrap up.
Unmuted. All right. Hopefully you guys made some progress on sitting. Oh, okay. No problem. Gonna wrap things up. I should share my screen and get set up. Oops, sorry. All right, I think most people are back from their breakout room, so let's go ahead and wrap it up. So hopefully everyone made some progress on packaging up their packages and things like that. You have more time to work on this, throughout the day, today and tomorrow. And well, if you have any questions, obviously we're here to help troubleshoot. It's like Sarah said, it's a lot of little things you have to get right. So there's a lot of gotcha. So we're happy to help you with all that. In the last 10 minutes or so, I just want to do a brief demonstration of how you can do code profiling. And code profiling is the process of kind of analyzing your code as it runs. And you can analyze things like how long it takes for your code to run, what functions run the longest, what functions take the most amount of time, what functions get called the most, things like that. Try to understand what happens in the inner workings of your code as you run it. It's a bit of more of a niche thing for people who are writing packages that take a lot of computation time. Is something that you're interested in using in, but generally you might not encounter. So we're kind of leaving this as kind of a quick optional thing that if you're interested, you can dive further into, but we kind of just want to show you a little bit of how it works. So all the code that I'll be showing you today is in the Code Astro Day 3 folder. So if you go into Day 3, we're going to look at two specific files. One is this profile_orbitize.py. That's going to be the file that we're going to profile. And then there's this Jupyter notebook. That's the analyze profiler. So after we profile this code, we're going to analyze it with this Jupyter notebook. So here I'm going to open up VS Code, and I've opened up Day 3, and I've opened up the profile_orbitize.py file. In the doc string at the very top, it gives you some instructions for how to run it. But basically, the gist is you copy this command. So I go into my terminal in VS Code here, and I'll make it a little bit bigger. I cd into Day 3. And then if I just paste this code in here. So what this code is doing is that it will run this script profile_orbitize.py like how you could run any other Python script by calling it with Python profile_orbitize.py. It just adds two extra options. One is that it adds this -m_c profile. And what this does is this will attach this a Python profiler to your code, and it will analyze the runtime of your code as it's running. And this basically happen automatically. So it's a nice, quick, easy way to basically profile your code. And then the other thing is that you see there's a dash O profile output.txt. Basically it'll output all the data that it profiles into this text file, and we'll analyze this text file later. So I'm going to hit enter, and it's going to start running. So it's going to run the code, and it might take a little bit. Just want to mention one brief thing here as the code is running. If your code is parallelized, generally I recommend you to turn off the parallelization before you profile your code. This is because the profile doesn't effectively. It's complicated to profile parallelized code. And in general, when you're profiling code, you just want to look for like what functions take the longest in CPU time and what functions are called the most in terms of CPUs. So you don't have to worry about parallelization. Basically only speeds up your wall clock time, like how fast you as a person experience your code to run, because it runs multiple things at once. So generally turn that off, because the profiler outputs it's kind of confusing to get the profiler running on parallelized code. So I generally recommend avoiding doing that. But so Orbitize is a parallelized piece of code, so I have to set num cores equal to 1 in Orbitize to turn off parallelization for this to work easily. So this takes a while to run, but like any good cooking show, we already have an output already saved for us. So let's just take this one that we've already previously made, and we can open up the analyze profiler.ipython notebook. So when this thing actually finishes running, it will override this text file profiler output.txt, but we're going to use the one we've previously created beforehand just to save a bit of time. So to analyze the profiler, we're basically just going to use this. We're going to use this Python package called pstats. It comes with Python, so you don't have to install anything. And basically, we're going to import pstats and basically ask it to read the output of the C profile output. So you don't actually have to know what goes on in this text file at all. It's very complicated, and you don't have to worry about it. You basically import pstats and have it read in this file. So I can hit run. It's going to run that, and it's going to read it in. So we can. I'm going to make this a little bit smaller because it's kind of like a lot right now. So we can do. I'm going to show you two kind of main functionalities that you can use with pstats that you can use to analyze your code after it runs. This is, I'm going to explain this live, but you can follow along. This is the text or what I'm going to say. So you can do something like my stats.sort stats by time and print stats 15. So what this does is that it takes all of the functions that ran in the code that you profile, sorted by runtime. So the things that took the longest will be sorted to the top, and the things that took the shortest will be sorted to the bottom. And it prints out the top 15. And you might be wondering why we're only printing out the top 15, because if I hit run here, you'll see that it analyzed our profiler output.txt file. I'll make it bigger again. And you can see that in that call, we ran 14,045,952 function calls. So sorting by the top 15 here makes sense because you don't want to go through all 14 million of them. So what we've done here is ordered by internal time. That's what the sort stats by time does. And then we print the top 15. So the list has been reduced from 8,152 unique functions to 15 due to that restriction. And that makes it a lot more manageable for us to look through. So you can see things like, the first function is calc orbit. So this Kepler.calc orbit, which you also encountered in the debug activity yesterday. This thing was called 4,670 times. So that's what the in calls column means. The tote time means that our code spent a total of 60 seconds in this function aggregated over all 4,670 calls. If we divide 60 seconds by 4,670, that means that the time per call spent in this function is 0.013 seconds. So each call to calc orbit takes about 13 milliseconds wall clock time. And then, oh, sorry, this is the, sorry, I missed one crucial detail. So total time is the time spent in that function, not including calls to sub-functions. So this is just like doing things like 1 + 1 = 2, sine of something like that. But if you call a helper function like numpy dot product or something like that, that is not included in total time, but that is included in cumulative time. So cumulative time is the time spent, total time spent in calc orbit, including all calls to sub-functions. So this includes calls like numpy dot product, say like scipy optimize, things like that are all included in cumulative time. And then if we divide cumulative time by in calls, then you get the time per call. So a total of basically 30 milliseconds, 29 milliseconds is spent per call of calc orbit, and only 13 of those milliseconds is spent actually doing stuff in calc orbit, not including calls to sub-functions. So this kind of gives you a sense for how long a function can take. A function with a high cumulative time but a low total time means that it's basically something in another function that it calls is taking most of the runtime. A function with a high total time and cumulative time means that there's something in this function that's taking up most of the runtime in your code. So this is a way to kind of analyze these things. And you can basically look through like you can see there's a bunch of orbitized functions. There's like there should be some numpy function. There's like things like that. Let me see if I can find some. Like numpy array gets called 170,000 times, and it spends basically most of the time. We spent a total of 2.5 seconds doing numpy array creation, and you can see that the cumulative time is also about 2.5 seconds. So most of the time is spent within that function, not calls to sub-functions. So that tells us, like, if we can make numpy array faster, that could help our program. Another thing, this filtering generally is very useful. Another thing we can do is basically sort stats by time again, but then filter by only the numpy functions and print out the top 15 numpy functions. If I'm only interested in seeing like how many times I'm calling numpy and how much is numpy slowing down my code, I can basically do something like this. And here again, it's going to filter all 14 million calls. It's going to order it all by time. It's going to only look at the functions that are from numpy. So only 561 out of the 8,152 unique functions are numpy functions. And then we're going to pick the top 15 again of those because there's 561 and we don't want to look at all 561. So here you can see these are just all numpy functions. The numpy array math is called the most. Numpy.random is called a bunch. Numpy array, numpy zeros, numpy random, another numpy random, numpy repeat, numpy VC. You can look and see like which of the functions that you're writing that is calling numpy is called the most, how much time it is taking, and things like that. So that's one way to basically analyze the runtime of your code. We have an activity here. If you're interested in learning more about profiling your code, please do this in the afternoon or on your own time sometime to learn more about this. It's basically asking you to analyze this output that we create, this orbitized profiler output that we create, and just look at, try to do other analyses beyond the ones I just showed you here. But in general, the three commands that we run get you most of the way in terms of doing code profiling. And in general, you only want to profile things that take up a lot of your runtime. For example, if something takes up, say, 50% of your runtime, and you miraculously speed it by, say, a factor of 2, which is sometimes a lot, you're only improving your total runtime of your code by 25%. It's the speed ups become more and more marginal as you speed up the biggest chunks of your code more and more. So it's not so think about that trade-off in terms of person hours spent doing something versus the actual amount of code speed up you get from doing these things. So that's just the one word of warning I have, but otherwise Python has this really nice C profiler that you can use to profile your code and try to understand the runtime of your code if that's something that is important for you when developing your package. Okay, so that's all we had today. So we talked about code documentation, code packaging, and now a little bit of code profiling. So that's what everything I think we have for you today. We just want to remind you that we have, is there anything to remind? Dinner tonight. Okay, so just for the in-person people, reminder we have a dinner tonight at 6. I can talk about that in a bit. But otherwise, keep making progress on your packages. Try to get a first round of documentation and your code packaged up today. Oh yes, and on Saturday we're gonna have a show and tell where you're gonna pair up with other groups and try out each other's packages and things like that. If you're here and want to do that, especially people in remote land, please let us know so we know who to pair up with who. We know some people may not be able to make it on Saturday and things like that. So let your TAs know whether you'll be there or not on Saturday so we can organize the group's show and tell for Saturday. Okay. All right, so thanks everyone for coming for day 3. Had a great day 3. Hope everyone enjoyed it, and yeah, see you guys on Discord, and let's talk more tomorrow.